Welcome to the video Introduction to Semiconductors. I'm Annie P. Joseph from Jyoti Engineering College, working as Associate Professor in the Department of Electronics and Communication. We discuss today with the Introduction to Semiconductors. The materials are basically divided into three, that is the conductors, the semiconductors and the insulators. The electronics field play a major role with semiconductors, and we are more interested to know about semiconductors, and it is the invention of the semiconductors and the improvement of the semiconductor which has given a drastic difference in the field of electronics. So we just go through how this conductivity is improved from the basic semiconductor and how the conductivity is carried out in semiconductors. The semiconductors will have a conductivity which lie between conductors and insulators. They have a unique feature of having a bipolar nature. That is, the current can be conducted either by electrons or missing of electrons. The concept of electrons and missing of electrons will be explained to you later. The free electrons in the outer orbit are known as the valence electrons, and these valence electrons determine the property of the material, whether they are conductors, semiconductors or insulators. The valence electrons in different materials and their properties are discussed below. That is, the conductors have less than 4 valence electrons, and they are the examples like sodium and magnesium. Insulators will have more than 4 valence electrons, and examples are nitrogen, neon and sulfur, while the semiconductor has 4 valence electrons, and the examples of these materials are silicon and germanium. The energy band theory, this says that the solids are being divided on the basis of valence band, conduction band and the forbidden gap or forbidden band. Valence band, the energy band formed due to the merging of energy levels associated with valence electrons in the last shell is called as valence band. Now I would like to explain what this valence band is. Now when you take an atom when you consider it has got these subshells like 1s squared, 2s squared, 2p4, etc. depending upon the configuration that has been given. Now, a molecule with n number of atoms, all the atoms in 2s level will all form one energy, and the next orbit of all the atoms will form one orbit. So like this, all the orbits of the molecule will all occupy a single level. Each atom being given the configuration, the n atoms in the molecule will all occupy the same energy level. That is, 1s square of all the atoms will be at the same level, 2s square will be of the same level. So all these will be there, and then the energy band formed by these energy levels with valence electron will be in the last shell, and that is called as the valence band. Conduction band, the energy band formed due to the merging of energy levels with free electrons will be called as the conduction band. Forbidden gap or the forbidden band we call the energy gap which divides the conduction band and valence band are known as forbidden band or forbidden gap. The energy associated with forbidden band is called as the energy gap and is denoted and measured in electron volts. In conductors, the forbidden gap overlap and the energy gap will be large in insulators. In semiconductors, energy gap will be very small. The diagrammatical representation of these energy gaps are explained below. So when you look into this, we just discussed with the conductors. Now when you look into the conductors, this will be, the bottom one is the valence band. You have the conduction band very close to the valence band. The forbidden band is very small. They actually overlap. This will be the way in which they move. So at different atoms of all the present will all occupy the same level, and all the free electrons will all occupy the same level. So it is easier for these valence electrons to jump from the valence band to the conduction band. So the conductivity is very high. That is why these are called as conductors. Whereas in insulators, this is the valence band. The valence electrons are all in the lower level. The gap is very large. So it requires some amount of energy for it to jump from here to the conduction band. That is why the conductivity is very low and they are called as insulators. In semiconductors, these are the valence band. The electrons will move from the valence band to the semiconductors with a normal forbidden gap where they can be improved. So this gap, even though it is little large, conductivity can be improved by some process which is discussed later. So that is how the conductivity can be improved. Classification of semiconductors. The types of semiconductors are explained below. Semiconductors, the pure form will be called as the intrinsic semiconductor and the impure form will be called as the extrinsic semiconductors. In the impure form, we have two types, that is the N-type eccentric semiconductor and the P-type extrinsic semiconductors. In the pure form, which are nothing but the intrinsic semiconductors. At room temperature, the valence electrons, which are at the lower level, can acquire sufficient amount of energy to enter the conduction band to form free electrons. Under the influence of these electric field, these electrons form a current. A missing electron in the valence band leaves a vacant space called as the hole. The hole will also contribute to the electric current and the electron-hole pairs will be formed. So when an electric field is applied across the semiconductor, this pure form, conduction takes place by the free electrons as well as the missing of the electrons. So now when you look into come back to this diagram here. Now look into this diagram. Now when an electric field is applied to this pure form, these valence electron acquire sufficient amount of energy and they move to the conduction band. So this electron has moved from here to this point. So there is a missing of an electron there, and that is called as a hole. The concept of hole is actually not present in semiconductors, but it is the missing of electron. That is why usually we always represent this a hole as missing of an electron. There is no hole formation actually, just this missing of an electron is being termed by a convenient name as hole. So now when there is a missing of electron, the adjacent electron will come and occupy this empty space and there is a formation of this hole here. So this process repeats. All the adjacent electrons will come and occupy this missing electron and this process continues. And these electrons, when they acquire energy, they go back to the conduction. So the electrons are moving in one direction and the formation of the missing electrons are in the opposite direction. That is why we just assume that the missing of electrons are positively charged and electrons are negatively charged. Since electrons are negatively charged, we say that the missing of electron is positively charged. Actually, there is no hole formation, nor the holes are positively charged. It is this missing of an electron which has given this idea of having a positive charge. Now the impure form. So that is the pure form of semiconductor, which we call this as the intrinsic semiconductor. The conductivity is very low. So by applying some at room temperature, only a few valence electrons will cross the conduction band. So improving the conductivity of these pure semiconductors have given a drastic difference to semiconductors. That is called as the extrinsic semiconductor. Now the conduction capability can be increased by a process called as doping. That is, you add some impurity to this pure form, make it impure, and then this impurity will improve the conductivity. So those material conductivity will also add on to this pure form and improve the conductivity. So after doping, the material become an impure one or the extrinsic semiconductor. Depending upon the type of doping that you give to this material, there are two types, that is the p-type and the n-type. Now you are considering a pure form, and when pentavalent atoms, so we all know that the semiconductors with 4 valence electrons are all called as the tetravalent. Whether it is silicon or germanium, they have 4 valence electron in the outer orbit and they are called as tetravalent. So when pentavalent atoms are added to these pure semiconductor, then it's called as the donor doping, as each impurity atom will donate 1 free electron to the intrinsic material, and such impurity is called as the donor impurity. This makes the extrinsic semiconductor with large number of free electrons, and they are called as the n-type. Because electrons are negatively charged, this has been given as n-type semiconductors. The examples of such material are arsenic, bismuth and phosphorus. Now look into this diagram. So here you see the valence band, the conduction band and the donor level, that is the impurity level atom. Now when you look into this n-type, see you have taken a germanium atom. So germanium has 4 valence electron here. Okay, the covalent bond, they form the covalent bond. So this is the pentavalent arsenic, which is formed with 5 valence electrons there. So these 4 electrons of this impurity atom added will combine with the 4 electrons of germanium to form the covalent bond. And 1 electron of this arsenic is not able to form a covalent bond with germanium. They are free. It is a free electron. That is why we call as free electron. So if more number of impurities are added, the number of electrons become more and the conductivity is improved thus. That is why we say it as n-type. But remember, by adding more impurity, this n-type semiconductor is not negatively charged. It is a neutral atom because the impurity arsenic is not leaving this free electron from its parent atom. So it is not free. When only electrons are completely removed from that material, they become negatively charged. So these n-type material, even though they have more electrons, they are not negatively charged. It is a neutral element. Next, we come to the addition of trivalent atom. When trivalent atoms are added to the pure intrinsic semiconductors, it creates more holes and will be ready to accept an electron. Hence, this type of doping is called as acceptor doping, and this results in a p-type extrinsic semiconductor. The examples of such material are gallium, boron and indium. So now we look into the diagram. See, when you look into this diagram, see here the valence band, the conduction band. This will be the acceptor level of your impurity atom added. Now here, be careful with this. This is boron, which has got 3 valence electron. 3 of boron will add on to 3 of germanium, forming the covalent bond. So 1 of germanium valence electron is not having a covalent bond. So it is missing an electron to form a covalent bond. So that is called as a hole. No hole is formed. It's just, that is why it's called as a hole. Be always sure with this. This is just a missing of an electron, and so it is just given as a name associated, missing of an electron as a hole. So now when you add more number of impurity atoms to this germanium with boron, more number of missing electrons are present. So this more number of missing electrons is assumed as a positive presence and given as a name as p-type semiconductor. The same way as n-type semiconductor is neutral, this p-type semiconductor is also neutral. This missing of electrons is just present within this atom itself. It is not formed out of that. So they are not neutral. The presence of missing of electron within this atomic structure is present, not outside. Only when it is outside you can say that it has been taken away from that atom, you can say that it is negatively charged or positively charged. So the presence of this hole is being assumed as positive, and then you call that as p-type. That's all. Because all these concept has come because electrons are negatively charged. Since electrons are negatively charged and the presence of more electron is there, so we have just given them as name as n-type. Since here electrons present is free electrons, the presence of free electrons is less, we call that as missing of electron, and we just call that as p-type. N-type extrinsic semiconductor. If a small amount of pentavalent impurity is added to a semiconductor, it is called an N-type extrinsic semiconductor. The pentavalent impurity has 5 valence electron. When voltage is applied to N-type semiconductor, the free electrons which are readily available due to the included impurity move in the direction of positive terminal of the applied voltage. This constitutes a current, and the conduction is by free electrons. The holes are less in number and the current is due to electrons in the dominant over the missing of electron. P-type semiconductors, the trivalent impurities like aluminium or boron and gallium is added to the semiconductor to get a p-type extrinsic semiconductor. These are called as the acceptors because it accepts free electrons in place of holes. The free electrons are also present in the conduction band but are very less in number, and the missing of electron, that is the holes, are the majority formation and the electrons will become the minority carriers. So this is with the p-type and the n-type formation. So next we have to see how this p and n are fused together and the current conduction is being carried out. Okay, thank you.